And first, a short reminder what happened. Okay, 2 weeks ago. So it was some discussion of the strong Markov property of the Brownian motion. Which basically says that, okay, if we have a stop in time, then the increments after that time are distributed exactly in the same way as their independent Brownian motion started at 0. Then it was an immediate corollary of this fact, which is called reflection principle. Which basically says that, okay, if we have a stop in time, and say here, and reflect the trajectory at this moment, say this way, then what we have is again, I mean, if we just think about the yellow trajectory, then it's distributed as the Brownian motion again. Okay, so this is distributed again as a Brownian motion. And then it was a corollary that for any given t, the random variables mt, which is the notation for the maximum over 0t mbs, mt minus bt and the absolute value of bt are all distributed in the same way. Identically. Okay, have the same laws. Okay, good. So what I'm going to discuss today, I mean, to start with today, is a sort of a discussion of these objects, mt minus bt, and absolute value of bt as processes. I mean, not at a given time, but just as a process over the whole line. And it's clear that if we wonder, does these processes, I mean, do, for instance, this and that, have the same distribution, or say this and that for the first and the second, the answer is trivially no, because this is something growing and this is something that bounces at 0 time to time, right? So, okay, good. And another reminder, just, well, okay, let me skip it. I mean, how to see from the reflection principle that, say, this and that are distributed in the same way. This is just a simple derivation. Okay, so, and the idea of the whole discussion I'm going to present is, you know, to switch between discrete and continuum. And again, what I suggest to have in mind is not this particular course, because there are many ways to present results on the Brownian motion, but instead the whole program when we speak about some discrete systems and their eventual continuum limits. So and just think about simple random walks and Brownian motion as a sort of the basic illustration. Okay, so in a sense, one of the first goals for today is to understand that the second and the third processes are actually distributed in the same way. I mean, as functions. Okay? So, and okay, it's going to be a theorem. again, you know, if you think for a minute, okay, both are positive time to time, each of them is 0, so there are some chances. Well, they might have indeed the same distribution. So here is the sketch of the proof. And details are left for exercises. But just, you know, I think what is important here is just to have an idea how such statements can be proven. And the idea is that you can model everything in discrete. So just in discrete. Consider two simple random walks in Z. Okay. Say Sm and S prime M. Two independent simple random walks in Z started at the origin. So those are just sums of independent Bernoulli random variables. So absolutely nothing, nothing non-trivial. And then claim is the following. So again, let M capital M be the maximum of Sm over the first segment. And the claim is that what should I write here? Just Sm. So this is the maximum over 0M of Sk. That this pair considered as a whatever discrete, as a process in discrete time is distributed in the same way as well, what is tempting to write, I mean, having in mind our goal, it's tempting to write just the absolute value of, say, S prime, right? So it would mimic this statement, you know, just literally. Well, actually, this is not completely the case. So what is the proper replacement is, okay, this process. Just why, say, the absolute value of S prime doesn't work? Just because there are some steps when we already have, when this is 0, right? And we're already at the maximum point, and then we do another step up. So at this time, this difference doesn't change, right? So if we just put modulus of Sm, it doesn't work, obviously. And the other component I denote by L prime. So what's that? This is just the number of indices such that, I mean, less than n, such that Sk minus 1 prime, Sk prime, and 0 minus 1. Meaning that one of them is 0 and the other is minus 1. Okay? So this is a simple exercise to check that it does work.
It should be maximum, the second one in the first bracket?
It should be absolute value. It should be maximum, yes. Yeah, it should be maximum, thanks. Yeah, thanks. Never remember. It should be maximum, of course. So, yeah. So this is a growing function, and this is again a growing function. So what I count is the number of the steps here. Okay, this is A. And provided we have such a discrete model, then basically what you do, you just apply Donskoy's theorem. So you rescale everything, nothing interesting happens because okay, you just rescale time and multiply all the processes by some factor in space, and then apply Donskir's theorem. To get that all the finite dimensional distributions that for any finite collection of points, for instance, this is distributed exactly as, you know, this is the limit of these guys, and what's on the right is the limit of those guys. Okay, and this 1/2 it just disappears because of the scale. And then you say, okay, I know that all the trajectories are continuous, almost surely. So if I know that all the finite dimensional marginals are the same, then I'm done. Yeah?
Do you only need the fact that the first components are distributed in the same way in the claim?
Ask again?
Do you only need the first component distributed?
Yeah. I mean, so what I used here is that the first components are distributed in the same way. And what I'm going to discuss now is what are the second components. So this is a good question. So actually what this isomorphism says is more than just this process is the same as that process, right? So we had some two-dimensional process, and then we just, you know, threw away the second component. So if it was your question. Yeah, good. So details are basically for exercises. Here, this is just a straightforward check. You just draw pictures and you see it works. Here, there is nothing deep because the maximum is a continuous function on the set of trajectories. This is, say, MT1 is a continuous function on C0 T1. So, well, okay. Here we are. So what is the discussion of the second component that I've been asked about? Some remarks. Oh, I'm again in the same catch. Where should I write? Maybe I should just delete this one and then have the same problem. Okay, let me erase this one first. So the first remark we already discussed. So we used only the first component. And what is very tempting is to say that actually there is an analog of this statement for the Brownian motion itself. The answer is yes, there is an analog. So actually, well, a stronger fact which is called Levy, well, another Levy theorem, Levy isomorphism theorem, if you wish, which says that, okay, you can write MT minus BT MT distributed as, here we have no problems, just the absolute value. And what is here is some process. Intuitively, what we should do, we should count the number of times we visited 0, right? In continuum, this is not a very good object, because Brownian motion, okay, if it's already 0, then there are infinitely many zeros just to the right. Okay, so maybe you could say, okay, maybe this is a number of crossings or something like that. Or maybe some another thing. I'm going to discuss it a bit at the end of this lecture, I mean just today, some process which is called local time 0. So we are going to discuss this in more details. And now you can think, okay, here I put 0, maybe it was for some purpose, right? So maybe we can do, if we are able to define such a process at the origin, maybe we can also define such a process for any other level. Maybe we can then think about the whole collection of these processes, etc., etc. So just right now, this is a very important object. And this is the first time we see it. Okay? So the second remark is the following. So let us introduce two random sets. Well, yeah, I must erase it now. So the first set is just the set of zeros. And the second set of the Brownian motion. And let it be Z, just the set of zeros. And the second set is the set of times when we renew the maximum. So those are just zeros. And those are what people called records. So this is a time when we set a new record. If it's a proper verb, set, what do we do with records? Okay, is it clear? I mean, the definition. Then what we know from the result I raised is that, okay, this is the set of zeros of the absolute value of Bt, and this is the set of zeros of the process M minus B, right? So what we know is that these random sets are identically distributed. Okay? Just because, okay, it's described by Bt0 is described by Mt minus Bt0. And the trivial remark is that these functions are continuous, so the sets are closed. So both are closed. So if you wish, you can think about metric space of all whatever, just introduce a cutoff, think about 0t, I mean 0, 100, and think about the space of all closed subsets of this segment. This is a proper metric space if you equip it with Hausdorff distance. Okay? Good. And yet another comment here is the following. So it's fairly easy to see that, let it be C, remark C. It's fairly easy to see that MT grows exactly on R. What it means? It means that T is in the record set if and only if you see that all the maxima, when you slightly enlarge the interval, are strictly greater than the maximum when you shrink the interval, right? Is it clear? I mean, why it happens? So just imagine here we arrived. I mean, we had some trajectory, and we arrived at its maximum. Then, after time epsilon, you know that there are points, almost surely there are points which are strictly above. Okay, so this is going to be strictly bigger. Another way around. So if you are not on this set, it means that, okay, you had some maximum already passed. So you are somewhere here. And then basically MT is locally constant. Okay? So basically what MT does, well, okay, yeah, it's written. I mean, it grows on this strange set. And then the intuition is that probably it should be the same, like here there is a set R and the process MT here. So this is the set of its growing points. And it should be more or less the same for Z and the local time at 0. So this is the picture you should have in mind. Yeah? Are there any questions so far? Well, if no, let me then switch to some computations for some time. So this is the next. Paragraph. Which is called Erskine laws. And this is a very classical statement. So again, there are many, many ways to prove it. And so this is a theorem. As far as I understand, again, due to Levy, but it has another name, Erskine laws. So, okay, what is the theorem? So the theorem is that for a standard Brownian motion, there are three variables. I mean, just think about this Brownian motion up to time 1. We do not need the future. So the following variables are distributed identically, and moreover, you can compute the distribution, are Erskine distributed. So what is the Erskine distribution? Basically, it's on 0, 1, and the probability that this random variable is less than t, this is absolutely continuous distribution, is 2 pi Erskine square root of t. Let us check it. I mean, there is much simpler interpretation of what's going on. So basically, what you should do, you should just sample a uniform random variable on 0 to pi and compute its sign squared. So alpha is uniform on 0 to pi. Hopefully, what you get is this formula. So, but the idea is that you just, okay, you sample a random angle, and then yes, well, and here it is. So basically, if t is 1, hopefully this is pi over 2, and everything cancels out. Good, so what are the random variables? The random variables are here. So the first is just the portion of time you spent above the 0. You spent in the positive area. And this is the Lebesgue measure. The second is the time you, well, okay, you had the last zero. So this is the supremum, or actually maximum of all times. Such that bt is 0. Okay, this is the last zero before 1. And the third is, well, you can guess it should be the same variable in terms of maxima, in terms of records, right? This is just, say, that's how people typically write it, but of course this is just formalities. And actually, we do not need any infimum or supremum here. So the statement is that basically there is only a unique time when you attain a given value. So here is the remark. So such a time is almost surely unique. Why? Why do we know this? Any ideas, by the way?
Otherwise we have 2 times, and after one of those we're going to go up. Sure.
Yeah, that's true, but yeah, well, that's good. There is a slight problem. The slight problem is that this is not a stopping time. Because to know that you are here, you should know what is the maximum afterwards. Okay, this is a very good intuition. Well, formally it seems it doesn't work, right? So do you see the problem? Yes. Yeah. So it's not a stopping time. I mean, well, there is a very simple proof. So actually, and again, this is also not a stopping time. So. You can think even more generally, so let us just think about all the local maxima. So just think about all the local maxima, meaning that I take any segment, and then I have a continuous function on this segment, and it attains its maximum value somewhere. So here is my maximum. And then what I'm saying is that even the set of all these values, yes?
So how about, like, on 2 different intervals, if you compare, like, what this is saying is that there's 2 open intervals so that the maximum is the same on both of them, right?
Yes.
But the distribution is continuous?
Yeah, exactly. Good, very good. So this is exactly the argument I'm going to present. So basically, if you compare 2 local maxima, say, one here and the other there, the claim is that they're almost surely different. Why? Just because that's what Hannah said. So just because if you write down difference of these 2, then okay, something happens on this interval, so you can write it like this. Just to compare it with the right end. Okay, it was the right interval, so with the left end. So this is just the difference of this value and BP prime. Then you have some increment which is absolutely continuously distributed. Right? Because this is just a Gaussian variable. And then something happens on this interval. So basically, since this is absolutely continuous distribution, the sum is also has an absolutely continuous distribution, so the probability 0 is 0. Okay? Is clear? And moreover, you can do you can do exactly this for all the rational intervals. There's a countable set. And all the local maxima of this function are there. And the values are all different. Okay? Just simple error. Well, and in particular, this time is almost surely unique. So, say for your argument, think about the simple random walk. All the things with Markovian properties are exactly the same, right? But then it might happen that there are several times when we actually attain this maximum. Well, it's cheating. I mean, not but okay. Yeah, I'm cheating here. Okay, so let us prove the theorem. Well, the most, I mean, if you do not think about the distribution, about the concrete formula, the fact that the second and the third have the same distributions, have the same laws, is morally trivial now, right? Because this is basically the supremum of what? Of Z, and this is the supremum of R. And this is supremum of Z. Cap 0, 1. This is supremum of R. No space. 0, 1. But the first guy is something different, and basically let us just discuss why T1 is distributed in the same way as one of them. I guess is T tau 3. And again, the way to proceed is to consider a discrete model for this. And it was a statement in exercises. So, see exercises. That for any random walk, and what I'm going to play with now is not a simple random walk, but rather a random walk with Gaussian increments. So, just consider random walk with Gaussian increments. Remember that it actually gives me, I mean, if I take 2 to n steps and rescale everything, then it gives me exactly the values of the Brownian motion if I use the Levit-Celsky construction. Okay? So, and for such random walks, there is just a combinatorial statement that the number of k's such that we are positive. Okay, yes. Let me also rescale and write it this way, because I can always think about this value as just, you know, it's about sk. The number of such steps is distributed exactly as k where we attain the maximum. Again, if a single step is not diffusive, then it's better to put here something like minimum. But with Gaussian increments, it doesn't matter, okay? Because all the values are different, almost surely. And this is just a combinatorial statement. So what you do, you rearrange trajectories in some clever way. Okay, this is an exercise. But essentially, this is more or less what we need. Right, because now what what I would like to do is just send n to infinity. So this is the claim. And now let n goes to infinity. What happens with the right-hand side first? What I claim is that it trivially converges to tau 3, almost surely. Why? Well, because this maxima converge to M1, right?
Normalize something.
Well, it depends. I mean, I already formulated the claim in terms of the Brownian motion.
But
You need to divide k by 2.
something.
Oh, yeah, here, yeah, indeed. Thanks. No. No, yeah. So I should normalize here. Indeed, I should multiply by 2 to minus n. Right, thanks. Yeah. So this just converges, right? And because of that, if I have a sequence of k's, basically what I see is that the values of b at these points, they approximate the maximum value, okay? Which is attained at a unique point. If I denote it, say, Kn, then this goes to 1. And I know by this remark that this point is unique. And what happened with the left-hand side? Of course, I would like to say that it converges to tau 1. There is a small caveat here. In principle, so what I'm just counting is the number of dyadic rationals where I have a positive value. What could be a problem? Could it be any problem? It could be a problem if B is so. Okay, let me just write it down instead of trying to explain in words. So the claim is that this okay, even the lower limit of this is greater than the Lebesgue measure of points where B is positive. And this is a trivial statement because this is an open set. So I can approximate it from below just by finite. This is an open set in a line, just by finite collection of intervals. And for each of the intervals, of course, I just count approximately its length. I mean, if it's a finite collection, then okay, it holds. And since I can approximate any open set by a finite collection of intervals from below, it holds also, right? And similarly, you can play with the indices where B is negative instead of positive. And so what you see is that, okay, this, I mean, the only option could be that this limit, I mean, the actual limit is actually, in fact, strictly greater than this measure. But then it would be a contradiction with the fact that we have no points where I mean, Lebesgue no points where the Brownian motion is 0. So I'm going to comment to say a word on this in a minute, but just to conclude the proof, right? So we know this. We know the same statement for the moments when B is strictly less than 0. And then we know that the sum of these terms is 1, and the sum of these terms is also 1. So because of that, all the limits exist. It's clear the technicality that happened here. Not that much.
In particular, by this we prove that we actually have not only, like, we actually have a limit of 2 to the power of minus n.
Yeah, exactly. That's what I'm saying. What I'm saying is that a priori, I mean, you might be not very comfortable with this random variable. What I'm saying is that the lim inf is greater than the measure of an open set is simple. You just think about finite union of intervals instead of this set. Then this is the first year class exercise, and then you approximate your set from below. Then you say, okay, I have the same statement with another inequality. Then how this cannot exist? What can be a problem? The only problem can be is that the sum of these two guys are actually less than 1. But this is not the case. Why? So I need to finish the proof somewhere, maybe just above. Why? Okay, what is the measure of the zero set? What is the expectation of this measure? So this is some random variable, so what's the expectation? You just use Fumini. So you have now two integrations, basically. One integration is over the probability space. The other integration is hidden here in T. So this is the expectation of the integral of the probability that, of the indicator that bt is equal to 0 dt. And you know that the process is actually more than just a collection of variables, that it's actually measurable with respect to the product sigma algebra. So you can interchange this expectation with the integral. But that's not the whole proof, because what I did, I just showed that all the random variables have the same distributions. And what we still need to do is to compute what it is. And what I suggest is, okay, this is an offer you cannot refuse. I grab another 5 minutes and we finish the proof of this theorem. So here what I explained is that indeed this strangely looking variable is distributed in the same way as, say, tau3. And the only remaining part is to compute the distribution. And basically it's fairly easy, modulo what we already know. So now let us compute it was tau3 somewhere. Let us compute the probability that, say, tau3 is less than some t. So this is the probability of the event. We have a maximum. So what does it mean? It means that M1 is attained on 0t, right? So tau3 is the moment where we attain the maximum. And so this is the probability that the maximum over 0t bs, say, let me put here bt, is greater than the maximum over t1 bs minus bt, right? And then we know what are the distributions. So the distributions, distribution on the left, this is just mt minus bt. And distribution on the right, you can put brackets here, parentheses there. And this is just the distribution of b tilde 1 minus t. T is now a fixed moment, so what I use is a weak Markov property. What I use is that after this time, what I have is an independent Brownian motion. And then so that's not B, that's M. Sorry, that's M 1 minus T. And then basically this is the probability that I replace everything by the modulus of BT because it's identically distributed. It's greater than the modulus of 1 minus T. I know that all these three guys are distributed in the same way. And then I rewrite it as BT squared greater than B1 minus T squared, or where both xi's are standard normal variables. Okay? And then what I say is that it's fairly simple geometrical problem because I can think about xi and xi tilde there is a Gaussian vector in the plane. And so if I rewrite it like xi squared over xi squared plus xi tilde squared is okay, tilde is less than t, then hopefully I'm done. I hope this is equivalent. It should be simple computation. But then I'm done because I know the distribution of this guy. This is exactly sine squared. Where's sine squared? It was somewhere. It was here. It's clear what happened? Just, you know, just centered Gaussian in the plane. Okay, fine. This is the end of the proof. And we have a break for 10-something minutes. So here, let us continue. Actually, I've forgotten to say in the name, I mean, when naming the paragraph, I've forgotten that it's going to be a sort of an addendum. Let it be here and uniform. Sorry for this. So our sign laws are for the Brownian motion. But actually, in many cases, a more natural building block is not a Brownian motion, but a Brownian bridge. Say in the models we are dealing with in random planar maps, I suppose you have a course on this in the spring term. So Brownian bridges are very important. And then the question is if there is any counterpart of this theorem of the Erskine laws for the Brownian bridges. And the answer is yes. So it will be here. Let now BT be Brownian bridge. Then still it makes sense to, it's dangerous. Still it makes sense to ask about what is the portion of the time we spend above zero and what is the last And what is the point we attain the maximum? So then τau1 is the measure of t such that what t positive, and τau2 the infimum, but actually you can erase it, of times such that bt is m, which is now maximum. Just maximum. They are distributed identically, and the distribution is uniform over 0, 1. This is just a small addendum. I'm not going to give a proof. So just some sketch. Again, this is for exercises. The third random variable now is meaningless, right? Because Brownian bridge is by definition something that is pinned here. So it has no last 0. Well, there are two parts. First part is that these two variables have the same law. And you can imagine that, again, this can be deduced from some discrete considerations. Again, this is the case. So, exercises. And then the question is how to compute one of them. And again, you can imagine that the second is simpler, so similarly to what happened with the Brownian motion itself. And here the idea is actually very, very simple. Let me just mention it. What is a Brownian bridge? There is a more invariant way to think about this. Just think about all the whatever trajectories of a simple random walk over the circle. This is some function which is defined on a circle, or if you wish, which is just periodic, like this. Okay? And then ask what happens if you now shift the origin. If instead of considering 0, you now consider some other time u, and think about this trajectory. Of course, what you expect is that you again have the law of the Brownian bridge, right? Well, it shouldn't be anything deep here. But then what happened with the maximum point? Say here, it was here. Well, now the maximum is attained not at some time t, but basically at t minus u, or 1 plus t minus u. Everything is mod 1. So, okay, good. Why should we expect that the distribution is uniform? Just think about a random shift. That you first sample a uniform random variable u and shift your trajectory. What you have is still the same law, right? Because for any fixed u, you have the same law. But then the time where we attain the maximum is shifted uniformly over the interval. So it's fairly natural that you have the uniform distribution. Okay, just idea. Shift time by some random uniformly distributed variable u. Is it understandable what I explained? Good. So now let us spend some more time in discussing the zero set of the Brownian motion. So that's the next goal. And the main idea here is not to discuss this set. Okay, this is a bit perverse sounding, right? The main idea is to give you more intuition about what local times are, because this is an important concept, and okay, it can be illustrated on a fairly simple material, actually. So the main idea is to get some intuition about that process LT0 which is not defined yet rigorously. So, okay, this is the next paragraph. Voila, 4.5. Some discussion of the zero set, of the set of zeros, of Bm, Bt, and okay, and that's it. And the local time, but it's not defined yet. Basically, I'm going to prove some result even here. So, and the result is about the Hausdorff dimension of this set. So, first, so reminder, Z is just the notation. And trivial remark is that it is closed. Everything is almost surely closed just because this is the Bt is continuous. Second remark is that it's nowhere dense. What does it mean? It means that for any interval, there exists a subinterval other way around, right? Which does not, which does not contain any point of Z. Why? Why it's nowhere dense? Well, it's trivial. Basically, if you have an interval, you know that there is at least one point where the Brownian motion is non-zero. What do I write? I mean, this is I, and here it was a trajectory, and it was a non-zero point. So around this point, there is another interval. And yet another remark is that it has no isolated points. Again, almost trivial, because, for instance, let us take some p and consider the first zero after p. Any such point cannot be isolated from the right, because this is a stop in time, this is a Markovian moment, and once we are at the origin, we have infinitely many zeros just to the right of us. Okay? It's not isolated from the right. Okay, probably it's tempting to say that the proof is done. Actually, not yet. Why? Just because we know that there are some zeros which are isolated from the right. For instance, pardon?
The last one.
The last one before 1, for instance. It's definitely isolated from the right. But the idea is that if, say, t is in Z and it's not a zero of this sort, then this is a limit, this should be a limit of such zeros from the left. And so the picture you should have in mind is this guy here. Okay, good. So this is a nice set. And then the theorem says that almost surely has the concrete Hausdorff dimension. You can guess which one. Any guesses?
1/2.
1/2, of course. Yeah, everything here is 1/2. So 1/2. Do we need some reminder on what the Hausdorff dimension is? Should I? Yes. Okay. Just reminder. So if you have, well, given alpha, say non-negative, let it be strictly positive even, and some set E in the metric space, let it be in the real line, well, in metric space, you define the quantity H alpha delta, which is by definition the the infimum of all of such sums where E is covered by the union of balls and all the radii are smaller than delta. So you try to cover your set by metric balls, and what you compute is not, say, sum of R squared, but this. Okay? And then this is H alpha delta of E. And then you define H alpha to be the limit. These guys. Actually, when delta decreases, so you just, you have less and less possibilities because of that, these quantities increase. So, okay, this is this is increasing when you refine the mesh, not the mesh, but the allowed size. And then this turns out to be a measure. It's called Hausdorff measure of order alpha. Alpha Hausdorff measure. And then this is a simple lemma that if you draw a plot of dependence of this H alpha from alpha, it looks like, this is a rather boring plot. This is plus infinity if alpha is small. This is 0 if alpha is big. And there is a sharp threshold. This is called Hausdorff dimension. So basically this is a lemma that if it's 0, then it's 0 everywhere to the right. If it's finite, then it's 0 everywhere to the right and infinity everywhere to the left. Okay, good. So it was a reminder. And and again, what I suggest to have in mind is that we treat in this example, we treat in this situation as an example, as an illustration for something more difficult, like for some ensemble of loops maybe in the plane. We're going to be in more than one dimensions, or for something of this sort, just to develop some intuition about the statements available around. So, okay, let me try to prove it. Don't think I need it. So, it's not complicated, but again, it uses some quite simple techniques you might not be aware of. And anyway, it's nice. So first take some beta, first either greater or smaller. What is simpler, smaller seems to be simpler. There I had a reminder, so what we need is to prove that H beta of Z is positive. So if I'm able to do so for any beta less than 1/2, then I definitely know that this threshold happens after 1/2. Okay? Good. So, all right, let us consider some covering. And let us, for instance, focus on Z01. Okay, let Z cap 01 be covered by the collection of balls, by some collection of balls with so what I need is to estimate the sum from below. Good. So, okay. What I'm going to write is the following. So, okay, imagine we have some collection of balls. Then what I know, let it be T. Okay. So the idea is the following. Here above this set, I have my, and I'm messing things up. Sorry. Sorry. Yeah. Let me include this record set into the theorem. It's distributed in the same way, right? So there is nothing deeper here. We know that this is the same as that. They have the same distribution. And so what I'm going to prove here is not that the Hausdorff dimension of Z is greater than not that the Hausdorff measure of Z is strictly positive, but rather that the Hausdorff measure of R is strictly positive. So what the set R is? The set R is the set where the function mt grows. So I have this function which is constant everywhere except this set. Well, something like that. The actual picture is more complicated, of course. It's a sort of a Cantor set. Then what I'm saying is that I know that this maximum process is a Hölder function, right? Because we knew that the Brownian motion itself is a Hölder function. And taking the maximum cannot destroy this property. So basically, since MT is a beta Hölder function. Yeah. This constant might depend on the trajectory. So this is some random constant. Depending on the sample. Yeah. I mean, right now nothing happened. I just said, okay, I have a way to control these R's to the B in terms of some function. But then I use the fact that outside of the set R, this function does not grow. And because of that, I can write that this is something very concrete. Which does not depend on the way I covered my set. So what happened here is MT does not go outside of R. Okay? Doesn't anybody follow? So, well, what do I know? I know basically that I have, for a given sample of my Brownian motion, what I have is the lower bound for this sum. It's universal, it does not depend on anything. It does not depend on the cover. Well, we are done, so basically it means that H beta M is H beta R is greater than some constant. And since it happens for any beta, or less than 1/2, we know the dimension is at least 1/2. So basically, the only piece of information, non-trivial information we used is here, is that the Brownian motion is Hölder continuous. So here is an important piece of information. Okay. It was the first part. And now, what is the second? Now let us take some exponent which is strictly positive, and then what we need to check is that H beta is small rather than it's big. Let us think about some portion of the zero set, saying between 0 and 2, or 1 and 2. And let us, so what we need to find is a good cover. So we need to cover this set so that the sum of R to the beta is small. So wanted good cover of this set. What is the idea? The idea is very, very straightforward. Let us just split this interval 1, 2 into many, say, n capital small pieces, and take all the pieces which contain at least 1 0. Just split it into n pieces of length 1 over n. And take all segments of this form, and let it be n capital, let it be 2 to the power n, all segments k2 minus n, k plus 1 to minus n, that contain at least 1.10. What I would like to say is that this is a proper cover, that if n is chosen large enough, then it cannot be that I have many zeros there. Okay? So, good. So what is there? What I would like to do is to compute the expectation of such a sum. Do we understand what it means? I mean, I just consider all the balls which are these segments. So what is the expectation? The expectation is, well, each ball has a fixed size. Well, first there are 2 to n balls, then each has a fixed size, 2 minus n, so I have 2 minus n beta. And then I have a sum of the probabilities that my zero set intersected with this small segment is non-zero. Well, actually, we know how to control this. What is the probability that on a given segment there is a zero or there is no zero? This dark sign law. So this probability is fairly explicit. Because instead, well, for instance, I can think that this is my endpoint instead of 1. And what I'm asking is what is the probability that the last zero is closer than 2 to the minus n to my endpoint, right? So what is the order of magnitude for this probability? Okay, all these endpoints are of order 1, so let me just think it's 1. Okay, the order of magnitude is basically, here we have 2 to minus n. So here we have square root because of this Erskine law. So this is of order 2 to minus n over 2. So altogether, what we have is that this expectation is of order 2n n over 2 minus n beta, minus n beta minus n over 2. So this is the expected number of these sum I should estimate, this expected value of this number I should estimate. Okay? And it decreases very fast. It decreases exponentially. And the rest is absolutely standard. So now apply Barrel-Cantelli to this. And claim that only, that there exists, okay, that only okay, that this sum is less than, say, 1 for all n starting with random n node. So the probability that this sum is greater than 1 is estimated by the same quantity, which is very, very small. It decays exponentially. So eventually what we have is that all these quantities, when we refine the mesh, are less than 1. Okay?
Question.
Sure.
When we apply Arc-Sine law,
Right.
what wasn't stated for like 0-1 segment?
Yeah, that's true. But what I mentioned is that let us think about not 0, 1, but 0, the right endpoint here. Let us apply Arc-Sine law to this. To this interval. The Brownian motion there is just the rescaling of the Brownian motion on 0, 1, and all the endpoints are in 1, 2. They're uniformly bounded. So basically the question, the order of magnitude is always the same. Okay? So it's always something 2 minus n over 2. And then what we see is that eventually we have a sequence of very good covering. They refine, and this quantity is less than 1. And so what I would like to conclude is that it means that h beta z cross z cap 1, 2 is less than 1. Sure. Question?
Why is it 2 to the 2n instead of 2 to the n plus 1?
Okay.
Why it's, well, because we are, what we focus on is the segment 1 over 2. So just because I consider here a restriction on 1, 2, not 0 to 1, 2.
Okay. So shouldn't the second bound be about twice the first one?
Yeah, summation is up to 2 to the power of n plus 1.
Oh, yeah, sure. Yeah, sure, yeah. Thanks. 2 to 2n is not 2 to 2n, yeah. Yeah, thanks. Well, okay, now we are done because what I proved is that the beta Hausdorff measure of the portion of my zeros between 1 and 2 is less than 1. So in particular, what I know is that Hausdorff dimension of the set is less than 1/2. And then it's a known fact that if you take a countable union of sets, then the Hausdorff dimension cannot jump. So if this portion has a dimension less than 1/2, if the similar argument shows that the portion between 1/2 and 1 has dimension no greater than 1/2, etc. So basically we're done. Okay, so this is just some result on properties of the Brownian motion. And let me conclude by some discussion of the local time I promised, of the local time at 0. So just here. So let me just mention several constructive, whatever it means, ways to define LT node. The most natural is the following. So we know that the zero set is the set of Hausdorff dimension 1/2. So it's very natural, just try this definition. Just take this Hausdorff measure of the intersection. So we know that the Lebesgue measure is 0, but maybe some other measure works. Well, this would be the nicest way to define it. Unfortunately, it doesn't work. Unfortunately, this is just 0. So, oops. It was such a nice idea, but it doesn't work. So, nevertheless, one can save it. Just slightly improving the gauge function and the definition of the Hausdorff measure. Just considering this log-log, yes. Well, it should be the same like in the Hintschen law, I think. Yes, log-log 1/r instead of square root of r in the definition of h. Well, it's slightly bigger than the square root of r. So if it's 0, maybe such a gauge function can help. Well, it helps. So this is a very, very constructive way. Just information. I'm not going to prove it. So the other way, if you saw something about Hausdorff dimension, then you should know that there is another dimension and another, not a measure, a content, which is called Minkowski content. And that they are not always equal to each other. So another way to save this is to consider Minkowski content 1/2 content. So what's the difference? The difference is that here you cover your set with the balls of fixed size. I mean, you just restrict yourself to the size delta. You are not allowed now take an advantage of adapting your cover to very small details. So instead of h1/2. Well, this is written, by the way. C Martins. For this, I don't know any reference, but Greg Lawler just last week told me it works. So ask Greg Lawler. Then there is yet another idea. Again, this is just to give you more intuition about this object. So yet another idea is the following. Just think about what is called occupation measure. So what is the occupation measure? You have some trajectory. It is a map from R to R. And you take the Lebesgue measure here and you project it onto the y coordinate. So take occupation measure mu t, which is defined is the Lebesgue measure of the set of TA is the Lebesgue measure of the set of times where BT is an A. This is a push forward of the Lebesgue measure using this BT. So each time you have a continuous mapping, you can even not continuous, even measurable. So you can do such a thing. You can take a measure and map it to there. So you have something on the y-axis, and then what's true is that fact mu t is absolutely continuous with respect to Lebesgue. This is not a hard claim. Again, just see Morter's Paris. Then a tempting idea is just to say, okay, let me take the density. If I have a measure which is absolutely continuous with respect to Lebesgue, then I can consider Radon-Nikodym derivative. The caveat is that Radon-Nikodym derivative is now defined only almost everywhere. I mean, okay, this is a bounded function, right? So we don't know anything more. So the particular value could be not defined. What we know is that it's defined for almost every A now, but maybe not for 0. So problem concrete A. And then, so somehow you can define, the bottom line here is that you can define the collection of such processes, but you are not very sure that a particular one is defined. And then the last and historically the first way to construct it, as far as I understand, is what I already mentioned, is to count, so just another 3 minutes, is to count some crossings of intervals near 0. So count down crossings of intervals. Now I'm going to explain what it means. So here is a trajectory. You fix 2 levels. Minus A, B. And then you define a sequence of stopping times. Let me do it pictorially. This is by definition tau 0. Then the first time we cross the above level is called sigma 1. The first time we cross the lower level after sigma 1 is called tau 1. Then this is sigma 2. This is tau 2. This is sigma 3. This is tau 3, etc. All them are stopping times. And then you say that the number of down crossings d a t bn minus an is by definition just the maximum of k such that tau k is less than 0. And then the formula is the following. Once properly normalized, these quantities do converge to something that measures the time spent in zero. The good question is why this is a proper normalization, and maybe we'll take a minute to discuss it on the next lecture, but in other context. For now, just if it's clear how the definition works. Question? Nope? Too complicated to ask? I mean, so yet again, so just 2 minutes, yet again. So we mark the first moment we cross the above level, then the first moment we cross the lower level after that, and so on and so forth. So this is here. Then for each choice of this strip, we have a random variable, just the number of down crossings by the trajectory. So this is a random variable. Of course, well, or not of course, I don't know well, but it seems that when we shrink this strip, it tends to grow. Why? Because everywhere near zero here, there are many, many small oscillations, actually, which we do not see on this scale. But when we take a closer look, then we see more crossings. So we need to normalize somehow. Well, here is a normalization, tends to zero. And the theorem is that such a limit exists. OK, so good for today. Thanks for being late. Any questions? Well, if no, see you next week. Yeah.
Why is it a good normalization? I mean, to the problem?
This is a good question. I mean, well, next week. Just think about it. I mean, the story is that what is the object you should think about? You should think about how much time you spend in between here and there, for instance. I mean, how much time does it take you to make one crossing? Nope, this is not a question. You should think about how much time you really inside of this strip when you are doing your crossing. This is some computation. I mean, you need to compute something. Then you just compare orders, and what you see is that it's a very good candidate for the Radon-Nikodym derivative, just for the density of this measure projected on the left. Because the idea is that it should be the density of the measure. So you should just count all these guys and project them back. Some of them goes from down crossings, some go from up crossings. It should be symmetric. So this is here 2 is exactly for this reason. And after that, there is a very good intuition why this is a good normalization, but you still need to prove this here. What I'm not going to do. OK, yeah, that's it.